episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
All right. Welcome everybody again to another episode of our show, profiling other fascinating guests that is all about creating a better tomorrow for all of us. So a little background, as we come to the end of this rather turbulent year of 2020, according to the National Cancer Institute, we had around 1.8 million new cases of cancer diagnosis in the United States, with over 600,000 deaths. Cancer continues to be a leading cause of death worldwide. As in 2018, there were 18 million new cases around the world, 9.5 million deaths. And the numbers, when we look at, are rather staggering, to say the least. We are honored today to be joined by Dr. Azra Raza, who is the Soon-Shiong Professor of Medicine in the Department of Medicine, Division of Hematology-Oncology, and the Director of the Myelodysplastic Syndrome Center at Columbia University Medical Center. Previously, Dr. Raza was the Chief of Hematology-Oncology and the Gladys Smith Martin Professor of Oncology at the University of Massachusetts. Dr. Raza is an international authority on pre-leukemia and acute leukemia, and is both a physician and a scientist who divides her time equally between caring for patients and supervising a state-of-the-art basic laboratory, which has been funded by multiple large grants. Dr. Raza started collecting blood and bone marrow samples on her own patients back in 1984. Now her tissue bank is the largest and oldest in the country, with over 60,000 samples, and considered a very unique scientific national treasure. Dr. Raza has published her original clinical and basic research in over 300 peer-reviewed manuscripts in a variety of high-profile journals like Nature, New England Journal of Medicine, Cell, Molecular Cell, and so forth. She has published over 1,000 abstracts, dozens of book chapters, and actually a whole book dedicated to myelodysplastic syndrome and secondary acute myeloid leukemia. She is a recipient of numerous awards, including the Hope Award in Cancer Research in 2012, which she shared with Nobel Prize winner Elizabeth Blackburn, named as one of the 100 Women Who Matter by Newsweek Pakistan. She's also a member of the Founder Group, which is designing breakthrough developments in science and technology with President Bill Clinton, and was also involved with then Vice President Joe Biden's Cancer Moonshot Initiative. And she is the author of a recently published book, The First Cell, and the Human Cost of Pursuing Cancers Last. And when she's not focusing on oncology, she is also a dedicated reader of Urdu literature, and we'll get into that in a little while. Dr. Raza, thank you for taking time out of your schedule to come talk to us a little bit today.
Delighted to be here, Ira. I have waited quite a while for this to happen now. Thank you for having me.
It's our pleasure. I'm so glad you're here. Typically, we start things off by giving our guests the floor just for a little bit to talk about themselves. If you could take a few minutes to talk about your background, a little bit about where you grew up, how you got interested in medicine and oncology, and if you would also, if you wouldn't mind, talking about your late husband, Harvey Priestler, who was not just your husband, but your research partner at Rush University Cancer Center. And if you could talk a little bit about that part of the story as well, I think that lays the groundwork for a lot that we're going to be discussing later on.
Thank you, Ira. Yes, I grew up in Pakistan, and one of 7 siblings. And even though basically the definition of a bum in my family was anyone over 18 not going to medical school, because 4 of my siblings did end up going to med school. It wasn't my first choice, because I really, from the time I remember, got really interested in nature, and was fascinated, for example, by ants for the longest time. Even as a 4- and 5-year-old, I would be following them around, got interested in, as soon as I could start reading, into evolutionary biology. And the problem that I faced when I finished high school and college was that there were no easy ways to get into a graduate study in sciences, basic science. And so the only way to pursue my natural curiosity was to enter med school. And I wasn't so sure I wanted to be a doctor, but because I wanted definitely to be a scientist, I thought, great, I'll just become a doctor and proceed to the West where I can pursue a PhD in molecular biology, and entered medical school. But of course, once I saw patients, one look was all it took essentially. Because from that moment on, it became very clear to me that every single thing I do, even in the pursuit of knowledge, would have to be somehow related to the service of humanity. Because the suffering is way too much, especially for cancer patients. And I got interested in cancer initially as an intellectual challenge, because it was just a most dramatic thing to see a normal cell. How does it become a malignant cell? And so malignant that it ends up killing a host. So basically, my story is that I joined medical school not wanting to be a doctor, but once I started seeing patients, that I was so moved by their suffering that I had no other choice but to pursue a translational kind of research, that therapy driven, that everything I look at must be through the prism of human anguish. And no matter how profoundly basic science question I was going to address, in the end, it had to somehow apply to the improvement of whatever we were doing for people. And so I came to the United States and immediately started working in a cancer research program, as well as a fellowship in oncology at Roswell Park Cancer Institute in Buffalo, where two of my siblings were already working. But then went to do my residency, finished residency, came back for my fellowship to Roswell Park. And that's where, when I arrived as a 24-year-old back in 1977, the first scientist in adult oncology that I met who was doing the same things that I wanted to do was Harvey Preisler, who was the head of the program, and became my mentor from that point on. And so I think that I can tell you very honestly, Ira, if I have 70 more lives, I would do the same thing 70 more times.
Thank you for sharing that. I appreciate you. I appreciate that very much. You know, as somebody that myself has spent, you know, a little bit of time on the sort of I'll call the periphery of the oncology space. You know, one thing that has always surprised me over the years is how much even our definition of what this thing, cancer, has become such a moving target. And the one area to me that specifically stands out is this whole concept of heterogeneity. The fact that in 2020 we are learning about heterogeneity at the genome level, how certain mutations can yield all different types of cancers, while single mutations or multiple mutations can yield the same cancer, heterogeneity within a tumor, and even heterogeneity amongst a patient population, pharmacogenomic, toxicogenomic differences, different microenvironments in my body versus someone else's. All this being said, when a field trip of kids comes into your lab today to look around, and someone says, you know, Dr. Raza, what's cancer? What do you say in 2020? How do you describe what cancer is with our current understanding of what we didn't know 40 years ago?
Yeah, you know, we keep talking about what cancer is, and it's very interesting that basically 150 years ago, all we could do about cancer was to be descriptive, that it is something where cells free themselves from the normal brakes which can be applied to their proliferation and growth. And once they free themselves of that, they just can continue to divide and grow forever. They become immortalized. I mean, that's the simplest definition of cancer. What cancer is unchecked growth and invasiveness. They can get out of the tissue in which they're living and invade other tissues. So that's what I would tell a layperson or children who come to my lab, who regularly do, by the way, even as young as 4th and 5th graders come. And the question was that 100 years ago, we were just describing basically what cancer cells look like, what they looked in the primary tumor, how benign tumors differed from malignant ones, and lots of descriptions. Guess what? Today we are doing the same except using molecular terms. That's it. That's the only difference. We are still don't understand what converts a malignant, normal cell into a malignant one. And we can talk about all the theories involved, but the idea is that we really don't know. And every time we think we know, we really don't. Something comes up.
As you've described the past in terms of not as much past. We still use these tools. You talk about cut, burn, and poison model, which dominated the oncology system for many decades, which we still use to some extent. Cared very little about differences in patients, differences in diseases, and we've moved to this very high cost, precision, smart drug era where we've created a range of therapeutic possibilities that look very good, but seem to only work in a very small number of people. And so we have a strange imbalance, and we still have these amazing numbers that I mentioned at the beginning of the show. Talk a little bit about your sheer view at this point, and then we'll get into some of the different things that you talk about in terms of strategies. Talk about where we've missed the boat in the war on cancer from your perspective of sitting there at Columbia, and what, why 100 years later, we are still in this environment of having this major killer, and still people asking the questions.
Yeah, that's a good loaded question. So you know that it was almost 100 years ago that Congressman Matthew Neely in 1927, almost 100 years ago, asked Congress to give him $5 million as reward to anyone who can provide information leading to the arrest of cancer. The point is that in the last 100 years, a lot of information has been provided, no arrest of cancer has occurred as a result of the information. Now, we keep talking about this War on Cancer Act by President Nixon. He declared war on cancer in 1971. In fact, it was again in 1937 that President Roosevelt signed the National Cancer Institute Act, and NCI, or National Cancer Institute, was created with just $10 million. Remember that Manhattan Project around the same time in 1940 something cost $100 million, but it was very focused. Now, we have had this ongoing war on cancer without either a coordinated frontal attack like was provided by Manhattan Project for the atomic bomb, without that focus, plus without giving freedom to individual investigators to follow their instinct into open-ended inquiry. And because of this one loss of this coordinated effort, and two, not allowing individual effort to really blossom, we have been losing this war on cancer. But by the way, I don't like this term war. So let's just talk about this for a minute. A war sort of implies that lots of people will be killed and there'll be carnage and a lot of blood and etc. However, the enterprise of cancer is a very noble one, because oncologists and basic research scientists are working so hard day and night to add to the knowledge base of what is cancer, to try and understand it and to try and counter it. So I would say that research that is focused on scholarly activities and in trying to improve the outcome for our patients should not be referred to as a war. And the reasons for losing the war then becomes a very problematic thing for me, because in fact there have been tremendous gains and improvements in our knowledge along the way about what cancer cells behave like, how do we tell a benign tumor from a malignant one with greater certainty, how we can basically the biological behaviors of different tumors have been explored, investigated, described, understood in such a phenomenal, profound way that I can't say that's losing a war. We have learned a lot, and today we are curing 68% of cancers that are diagnosed. The third of the patients that we can't cure is because they present with very advanced disease. And that is where we haven't made significant effort, significant gains. The questions I ask, and which you referred to also, is that, look, we are curing 68% people, but with what? The same treatments that were there 100 years ago almost. Why? Why has not the spectacular improvement in our biologic understanding been translated into improved therapies for cancer patients? Why this terrible disconnect between understanding and helping a patient? And what are we missing here? Those are the questions I'm asking.
Excellent, excellent. Let's move to one of the themes that you talk about quite often, and this is this concept of giving up the mouse, in essence. We have, I don't know what the numbers are, but we cure cancer in mice thousands of times a year, labs across the world. If those mice could pay, we'd all be very rich. Mice are not humans. For a variety of reasons. And take us on a little journey of what we're doing wrong with the animal models, and then if you could segue into your specific tools in terms of the history of your tissue bank, in terms of focusing on the human cells and the progression of oncogenesis that you can study at this level. Take us on a little journey there, if you would.
You know, Ira, a model is a lie that is supposed to help you see the truth. We started by treating cancer by just slashing at it. And the oldest known case of successful cancer surgery goes back to Queen Atossa, who lived 500 years before Christ. 2,500 years ago, this Persian queen felt a lump in her breast. She tried to ignore it, it kept growing, so she called her Greek slave, who took out his sword and simply slashed her breast. And she survived and lived to help her husband, Darius, for a long time. So this is the first successful case of mastectomy that has been described. Whether the tumor was benign or malignant, we won't know. But the question is, we were slashing breasts then, we are slashing breasts 2,500 years later still. So surgery was the only treatment for cancer, solid tumors. Then radiation was discovered, and so radiation therapy was applied, and these two were the modalities. It was only after chemical weapons were developed in the Great War. We called it the Great War instead of the First World War because we didn't know we were going to have a Second World War. So in 1917, chemical weapons were discovered, were developed, and there was an accident in Bari, Italy, and of course multiple soldiers got exposed to chemical weapons, and it was noticed that after exposure, their blood counts plummeted. And so the idea started taking root that we could use these chemicals to poison liquid tumors for which we couldn't use radiation therapy and surgery. So why not use these chemicals to poison? And do you know, Ira, that the first 3 drugs that were developed, Cytoxan, chlorambucil, and melphalan, all 3 I used with my own hands on my own husband now. So we're talking from the Great War to now, the same chemical weapons being used with very sort of unchanging results in a way. Now, it became apparent after a while that indiscriminately giving 1 or 2 or 5 combinations or multiple cycles of the same combinations without having any guiding principles behind was not going to cure cancer. So then it became apparent that we need to really understand the biology and try to figure out why some patients respond to chemotherapy and others don't. And that kind of thing then started to grab and grip the minds of great investigators and scientists who started to look into the biology of cancer. And very quickly, because it was all becoming molecular biology, the DNA had been discovered, and then the structure of DNA was discovered, and everything was being looked at that molecular level. This is one of the problems that happened, Ira, that we became very reductionist, and that reductionist conceit, as if a very complicated disease like cancer, which is an emergent disease out of a series of events that happen that can differ from patient to patient, from tumor to tumor in the same patient, that lead to this emergent complexity, and we are trying to deal with it as if we will find one gene that is making one abnormal protein that we can target with one magic bullet. And that the problem is that this paradigm succeeded in the beginning with 2 of the cancers. So chronic myeloid leukemia and acute promyelocytic leukemia proved to be one of these best case scenarios where one target was identified, and killing or attacking that target did produce cures, basically, in deadly cancers. And so this seemed to establish the paradigm for all. All we have to do now is to look at for this same kind of one gene or one target in pancreatic cancer, ovarian cancer, lung cancer, and then come up with one drug. It turns out that with time, as we have sequenced the human genome, we have sequenced hundreds of tumors, whole genome, whole exome sequencing, that there are thousands and thousands of mutations, and almost no 2 patients are alike. There are hundreds of driver mutations, thousands of passenger mutations, differing from time to time in the same patient, in area to area in the same patient. So the problem that we are facing now, Ira, is that the farther you go into the sea, the deeper it gets. The more we look into cancer, oh, it's not just the cell, it's also the surrounding microenvironment. Let's look at the microenvironment. No, it's not just the cell and microenvironment, but the amount of blood supply it's getting. So for a long time, 10 years, we were just trying to choke off the blood supply of tumors. Oh no, it's not just that, it's also the immune system. Oh no, it's the cell, the gene, the microenvironment, the blood supply, the immune system. How do you put all this together? These are all very complex issues. My simple, very you could say, in almost a naive answer is, listen, to enjoy my dinner, I don't have to understand how the digestive system works. In other words, to cure cancer, the best cure is prevention. To prevent cancer, we should identify its earliest steps, and why not just try? Because the only strategy that works is it's not cancer that kills, it's the delay in treatment. Only people who die are those who are discovered with advanced disease. We can cure patients with even existing techniques if we find them early enough. Why not set our sights for such early steps that we basically start monitoring wellness to find illness and then prevent it at a very early stage, because that's where it will be least complicated. This is my whole thesis, and I took you through the whole historical journey of how cancer treatment and research has evolved towards finally realizing that the problem of cancer is so vastly complicated. It's as if we are trying to cure aging. Yes, we may be able to cure aging at some point, but not for 1,000 years. And it's a very difficult solution. So while we are working on all of that, one should not be to the exclusion of the other. I'm not saying we should stop working on trying to understand all these complex issues I just enumerated for you. All I am saying is that we should also pay equal attention to what can we do for the patients today and now to help them, and what can we do for the ones coming. All of us are at risk of cancer. What if I get cancer today or in 5 years from now? What can I do for myself to try and have a better solution for this? And that only comes with how early can I detect my cancer and how early can I take care of it.
And you've talked about the principle of repurposing in the past. So basically, we don't have to create anything new. I think you've talked about metformin, Celebrex. Talk a little bit about the work that you've done in sort of repurposing research as you look earlier in the stage of these cell transformations based on your tissue bank, and also any of the some of these more advanced tools, artificial intelligence and whatnot, that can be useful when so many samples, and as you were mentioning, thousands of passenger and driver mutations across however many patients. Any of these tools useful in allowing you to sift through all this data?
Yeah, very insightful questions actually you're asking. So I began my career by studying and treating acute myeloid leukemia, AML. This is one of the deadliest diseases known to man. By 1984, it was clear to me that in my lifetime, this disease will not be cured. And I was right, because sadly, in 1977, I was treating acute myeloid leukemia with two drugs, popularly known as 7 and 3, because it was 7 days of one, 3 days of another. In 2020, we are still using 7 and 3. That is the frontline treatment today for AML. 44 years later, using the same exact thing. So, and with the same dreadful results. The only patients who survive are those we can take to transplant. But if you're an older person, transplant is out of the question. So your only hope is really 7 and 3. Otherwise, everything else will add a few months of survival here and there, and you die anyway. When it became very clear to me that this is too complicated a disease, I became interested suddenly in listening to my patients who were giving stories that sometimes months and sometimes years before they developed this acute myeloid leukemia, their blood counts had been going down. And so that's phase is called pre-leukemia. And that pre-leukemia is known now as myelodysplastic syndrome. So I said to myself, wow, I should have just caught these people when they were pre-leukemia, because the disease must have been much less complicated and easier to treat. So I turned my attention in 1984 to trying to study and treat patients with pre-leukemia and then following them as they develop leukemia or they died of their pre-leukemia without developing leukemia. At this point, had I gone to school in this country, I would have then turned to make a mouse model. But fortunately, I was a naive immigrant, and I trusted instinct over tradition and custom. And I thought very simply, if I'm going to study these patients, I need their cells. So I started saving their blood and bone marrow cells in my freezers. And that has grown into a tissue repository that is the oldest and the richest in terms of samples. We now have 60,000 samples. And do you know, not a single cell comes from another oncologist. These are all patients I have taken care of myself. To this day, Ira, I draw their bloods myself and do the bone marrows myself. It's like I work like an intern in my clinic to this day. And it is meaningful to me. Why? Because this is the only tissue bank in which I have saved longitudinal samples as disease progresses in individual patients from start to finish. And all kinds of samples, serum and plasma and biopsy and buccal smears and T cells and separated stem cells, etc., etc. So like you suggested, this is a very unique and a very rich source of material. And what I'm trying to do is to trace back the footsteps to the earliest events that happened in these patients and how the disease evolved using the latest technology of genomics, transcriptomics, metabolomics, proteomics, multiomics. Trying to use that, all of those technologies to find the earliest footprint, and then trying to see if in patients who have pre-leukemia, we can catch and trap the earliest leukemia cell that appears and move in to treat them as early as that first cell stage. How is this possible? Well, it's very possible to do all this with the technologies that have been developed. And so the tissue bank, having this retrospective possibility of going backwards in time, 25, 30 years, and having the entire clinical information available in a computerized data bank that accompanies the samples, we can literally put almost like a telescope and look backwards into their diseases. And once we find what were the earliest changes in the disease of this person who ended up here 10 years later, what was the earliest event? We can ask the question, why did someone who was completely normal even develop pre-leukemia? What was making them susceptible? What were the risk factors involved in this? And what were their germline DNA and RNA? What did that show us? You know, because I've saved germline samples on everybody as well. And so these are the questions that have to be asked, because rigorous science, very carefully conducted studies is the only way to really understand how to go to the earliest event. And no amount of magic or praying is going to help here. We need the science, we need the technology. But instead of using all our science and technology and resources, both intellectual and financial, to target the end stage disease, I'm saying we should divide them half and half to the end stage disease, because we have cancer patients today and we need to look after them and we need to come up with new therapies. But also the other half to trying to take it back to the first cell stage, and then trying to understand how we can then monitor healthy people to find that first cell and prevent it from becoming a bona fide cancer.
You know, thinking about the early, the pre-leukemia, or even the, I've heard you talk about, I forget how many, across the trillions of cells that were all made up of, I don't know how many transformations occur in a given day that our bodies naturally just deal with. You know, you and I, before the show, we were talking about some of the oncology ecosystem here in Philadelphia, and it got me thinking as you were talking about, you know, several miles down the road is the Fox Chase Cancer Center, where Beatrice Mintz used to be, who did quite seminal work on this principle of tumor reversion in embryos. And that was the 1970s. But if you go back before that, bringing into our early discussion about nature, it's been known for close to 100 years that many regenerative organisms, salamanders, flatworms, and so forth, are very good at taking very complex tumors and just turning them into normal, healthy tissue. I guess as humans, we're somewhat decent at that early in life, but not before tumors get too far. And this just got me thinking about early stage, looking at nature. Have we jettisoned nature a little too much in our study of oncology? Because a lot of these early drugs, even some of the current ones, the Taxols and so forth, come from nature. Have we jettisoned looking at the natural world for some clues in favor of doing things more synthetically or on the computer screen? And do you think nature still has things to offer us in 2020?
Yeah, excellent question. Listen, first, let me make one correction to what you said.
Please do.
We can cure acute myeloid leukemia in mice since 1977.
Okay.
You know how we cure it? Because it's not as if a mouse develops spontaneous acute leukemia. We try to create a disease we call AML because mice don't get spontaneous AML. We create something in mice and cure it and claim, oh, we have cured the leukemia. The same way, you are saying we can cure tumors that we create in all kinds of model systems. Yeah, but those are not tumors that appeared spontaneously. What's the difference? The difference is that spontaneously appearing tumors, there's something wrong with the host's immune system, the microenvironment, all kinds of changes. The way we produce a tumor in a model system is introducing cells that are abnormal or causing DNA damage by radiation or causing some stress that could convert the one cell into a cancer cell. And yes, then we can get rid of it. But when cancer actually develops spontaneously, it's a very different disease. It is so many steps so that the whole tissue level process cannot be predicted by simply a mathematical addition of various genetic events. No, the emergent property in a spontaneous cancer is very different. Now, what we have missed our boat in, though, is you see, the idea, one of the ideas about what causes cancer is that, yes, in some people there is a hereditary predisposition, in others there could be exposure to chemicals or toxins that could damage DNA, or in others it could be a pathogen like a bacteria or virus or fungus that is causing the problem. But in the vast majority, like 70 to 80%, we can't find any of these reasons. And we say it must be because during the normal process of doubling DNA, there are some copying errors that lead to mutations in some vital genes, and that mutation can lead to the cell expanding its own clone and escaping the growth inhibitory signals that a normal cell would respond to. So in other words, it's a random DNA copying error that leads to the formation of a single cancer cell. Now, if that is true, then the number of cells that are undergoing proliferation, if they are higher, chances of cancer should be higher. It means larger an animal, the more the incidence of cancer should be, because they have more cells dividing. So more cells can make mistakes. However, that is not the case, because do you know the largest mammals like elephants never get cancer?
Yep.
Blue whales never get cancer. So what are the natural protective phenomena that exist in blue whales and in elephants that we don't have? Well, in elephants, they said elephants have 20 copies of a gene called P53 that is supposed to inhibit a cancer or a cell from behaving in a rogue way and becoming malignant. So if we can have this tumor suppressor gene P53, it is present in many more copies in an elephant than in humans. In 20 more copies are there. So they said, well, why not try and increase the number of copies of P53 in a mouse and see what happens? Then we can see, we try to create cancer and it would be protective because it has multiple copies of P53. When we did that, we found that yes, we protected the animal from cancer, but the animal died of very rapid aging very quickly. Next thing they said is, well, maybe what we can do is let's just knock out the protein that is supposed to destroy P53 protein. So P53, even if it's one gene, the protein will be available for longer because the thing that's supposed to destroy it is now gone, MDM2. So a knockout MDM2 mouse is made. And you know what happens to that one? It melted in front of your eyes from excessive suicidal cell death in every cell. Because of excessive amount of P53 being present, it just forced every cell to commit suicide and the mouse melts in front of you. So when we make model systems, we even of phenomena that we think are protecting some animals in nature from getting cancer, we really don't understand it. We're looking at one gene, one single gene. That's not the case. And in blue whales anyway, there are not 20 copies of P53, so they have some other phenomena that protects them. This is called Pitos Paradox, by the way. The fact that larger animals don't get cancer. Why is that happening? And the solution to Pitos Paradox right now is that, yes, larger mammals like ourselves get a lot of cancer initiation. But what happens is, let's say a cancer cell begins because it made a random DNA copying error and it's now escaping the growth inhibitory signals and it's starting to divide. As soon as it starts to divide, it has to improve nutrition for itself. So it starts making or attracting blood vessels and more blood towards it. So it has to make some growth factors that will improve formation of new blood vessels. And what happens next is that a cheater arises within this population of cells. This cheater, because it has sustained another mutation, can divide even faster than the original cancer cell, but it doesn't make the protein that forms new blood vessels. So very quickly, its population takes over the original cancer, but because it is unable to make the blood vessels, the whole thing dies. So this is tumor formation, then hypertumor formation. That's what we think is happening all the time in our bodies to destroy the cancers. How can we, so when you ask me, well, have we missed something by not paying closer attention to how nature is handling these things, either in the initiation, progression, invasion of cancer, or treatment with natural herbs and whatever substances exist in plants and animals that we could find? My answer is yes, absolutely. We have used animals for the wrong reasons. We think we are creating a model with a tumor, but it's all really smoke and mirrors. It's nonsense to say that a lung cancer that exists in a human, you have created a lung cancer in a mouse or in whatever animal you're using, and treating whatever you created with a drug is going to work in a human now. No, I think what we need to do is have comparative oncology in which we do compare the spontaneously occurring cancers and study those animals like a naked mole rat who never gets cancer also, which is a small mammal.
Right.
And then you have large mammals like elephants and blue whales. Now, I told you that the elephants don't get it because they have extra copies of this tumor suppressor gene. A naked mole rat or a blind mole rat, both of these varieties of mole rats that live underground, very interesting social mammals. They don't get cancer because of hyaluronidase pathways that we have developed. So, I mean,
Right.
there are different reasons. And why aren't we having fellowships to study those? And in terms of treatments of cancers, many of the chemotherapies we use started as antibiotics that were extracted from fungi and bacteria and, things like
Yep.
that. Absolutely. I couldn't agree with you more, but I think that use of nature has been kind of very artificial and very simplistic. And
Yep.
we need to understand the complexity of cancer, the complexity of nature, and not be so arrogant into thinking that we can overcome all this complexity by simply understanding a few small parts of the story. No, the emergent property is far more complex than its individual parts, and that it will take us centuries to really unravel all of those complexities. In the meantime, too many people are dying. So what can we do about them?
Yep.
Sorry, I keep coming back to the same
No,
mantra.
I really appreciate it. I appreciate all this insight. It's fascinating listening to you talk about it. Moving from cancer to a related topic, let's say, you were quoted as saying, "The best way to tame the savageness of man and make gentle the life of this world is by promoting and publicizing the achievements of humanity in science, art, and literature." I completely agree with you. Take us on this part of your journey, please.
I know you're quoting that from my brother's website, Three Quarks Daily.
Absolutely.
So my younger brother Abbas has this website that he started about 16 years ago now, and it curates the best of the web on a daily basis. And I'm one of the sub-editors. I post at least 2 stories every single day except Mondays, and I've never missed a day in the last 15 years. The idea is that knowledge across disciplines, especially, is so critical. And the discourse has to be at such a level that it's not all just jargon, that consilience across disciplines becomes possible. And so we feel very strongly that the arts and sciences and philosophy and music and literature, everything has its own place, its own contributions. Pure science cannot progress without an imagination. For me, especially someone who is dealing with human beings who are facing very painful, life-threatening illnesses, I cannot simply rely on scientific facts to help those patients. In fact, I have to bring all of my intellectual, emotional, spiritual, psychological faculties to bear. Instead of, patients have a corporeal language also. Their bodies can speak volumes. Sometimes they are unable to verbalize their anxieties, their insecurities. Sometimes they don't want to know the bad news. How do you read this corporeal language? What is its grammar and syntax? To understand that, whose shoes should you be standing in? And should you be reaching into your own bookshelves to try and develop that empathy, that ability to feel what the patient is experiencing at some level? And that's the difference that I feel Turning to literature, for example, will make very obvious to you the huge difference between cure and healing, for example. You can't understand that without experiencing some of the torment that your patient is going through. You know, Emily Dickinson, beautiful. Tell all the truth, but tell it slant. Success in circuit lies. Too bright for our infirm delight, the truth's superb surprise. Like lightning to the children, eased with explanation kind, the truth must dazzle gradually, or every man be blind. Unless you awaken to this kind of an understanding of what humans are going through when they are facing mortality head on. There is no heroism in pain and suffering at that level, you know, unless you understand, for example, the kind of experience somebody had in a concentration camp. And now there is a concentration camp of the mind and soul and spirit, where you're constantly trapped in extreme pain that you feel, and horrors of that, of cancer that it can visit upon you, which I witnessed in my husband. Every single indignity that you could imagine happened to that poor man. And experiencing that at such close level also, I would not wish it on my worst enemy, really. But that kind of I can't say appreciation, but that kind of understanding, apprehension of the challenges of this disease, you need to have read Gatsby, for example, the Great Gatsby,
Sure.
Where even if there is a cure, that moment of gratification does not match the vastness of desire and all that was driving and all the pain that you experience in the entire journey. So what is the healing then that takes care of this violent, horrible, daily battles that you need to face with this disease? Those are the issues that I feel are so important.
Who, for someone like myself, and probably a lot of people listening that have no experience with Urdu literature, who was the poet Ghalib, and why did you write a book about him, or his several of his poems?
Yeah. Well, thanks for doing so much research on me, first of all. Most people have never read a word about me when they interview me.
I think I should do something.
You seem very well informed about Three Quarks Daily, about Ghalib. So Ghalib is a poet who lived in, he was born in 1797 and died in 1869. And so he was like a contemporary of Emerson, for example, or a contemporary of Emily Dickinson.
Yep.
And he's living in India, and the kinds of questions he raises, the kinds of physical and metaphysical issues that he addresses are universal, because those are the themes being raised by Dante or Shakespeare or Emerson or any of the great writers. And to me, the poetry, his language, and the culture that produced that language behind it, the courtesy culture, and then the intensity of his questions are so overwhelming and so dramatic that there is not one single problem I have faced in my life that Ghalib in some way or another did not address. So his complete works are in fact very narrow, 1802 poems, that's it. That can be in a very rather thin compilation, but in the space of 25 words or less, the man can raise questions that you can debate for forever and yet come up with reinterpretations every time you reread it. So that, I'll give you one example.
Please.
है गैब गैब जिसको समझते हैं हम शहूद, है ख्वाब में हनूज जो जागे हैं ख्वाब में. What we think has been revealed to us actually has remained hidden.
Mm.
It is like the dreamer who thinks he's awake, but is actually dreaming that he woke up, but is still dreaming. So in his dream, he woke up. That's how we are, the complexity. So this, for example, these two lines address the ultimate unknowability of the truth. That just when you think you know, actually you are like that dreamer who thinks he woke up, but he's dreaming. So in other words, don't become too complacent and self-satisfied with yourself, because you really don't know. Just when you think you know, remind yourself what, for example, Theodore Adorno said, that the highest form of morality is to be a little uncomfortable in your own home. This is exactly what Ghalib's message is here also. So these two lines, you can think and debate about these two lines, and you apply them to your daily working and interaction. Just when I think, oh, this gene is going to solve all the problem, no, tell yourself you are that dreamer. And in other words, remain skeptical, question yourself all the time. Do not think, and it makes you lose that arrogance that you'll ever know, in fact. Do you see what I'm saying?
Absolutely.
The more you think about this, and if you knew the language, of course, translation, you lose so much in translation, but the brevity and the frugality of his language is so stunning, so staggering, because you can't literally remove one word from a place to a second place, and you could lose the whole meaning. But Ghalib is the kind of guy who didn't belong to a party. He was living through the worst wars in India when the British, when the Indians stood up in what the British called the Mutiny of 1857, and the Indians called the War of Independence. They say that there was knee-deep blood in Delhi, in the area where Ghalib is living. And yet he never talks about war or, party affiliation or any kind of nationalistic or anti-British or pro-Indian rhetoric, nothing like that, because his concerns are for all of humanity much larger than all of this. These are things that happen in front of me, like games children are playing. That kind of a grand vision he has. So I really rate Ghalib up there with Dante or Shakespeare or Milton from the West, that names that you would recognize and would consider as some of the greatest poets. And in some ways, I recently gave a talk called Ghalib and Self-Reliance. And the whole idea of Emerson in self-reliance is a foolish consistency is the hobgoblin of little minds.
Okay.
And Emerson basically exploded the notion of self-reliance by saying the self is not something little sitting inside of you that is directing you, and that now you can depend on that self. That self is what has, what has interacted with the larger world around it. When that self-circulation joins the larger circulatory system of the universe around it through all its interactions, that is what defines who you are. So in other words, yourself is actually the whole world. In other words, to understand one person, you have to swallow the whole world. And these are the kinds of connections that that Emerson talks about. And then Ghalib goes one step further and explores the Emerson myth also. So, I mean, these are the grander issues of that we all face, the existential angst of all of humanity. What is it we are searching for? Why, if we have everything in this world, are we still looking for something? Is it separation from the deity? Is it a, what reunion are we seeking? What is the human angst? These are the questions that Ghalib has addressed, and I have only used with my co-author Sara Suleri 21 poems of Ghalib to try and, we can't translate, as I said, so much is lost in translation and some things are gained in translation as well, but we try to interpret the poetry.
Beautiful. One final question while I have you. About 5 years ago, you read a very touching letter from your daughter to your late husband at the TED conference. I noticed that your daughter narrates the audiobook version of your current book, and she's embarked upon a very successful career in science journalism. How's she doing? I noticed a lot that you were together quite a bit, doing things in the past. How's your daughter?
Well, thank you so much for asking. You know, that poor child has lived through a lot with her father being diagnosed with cancer when she was 4. He's dying. He died 4.5 years later when she was barely 8 years old. And then as her best friend, Andrew, who was her best friend since she was 15, not her boyfriend because Andrew was gay, but her best friend who gets diagnosed with this beautiful young man in and out of my house since he's 15 years old. You know how children are.
Sure.
And he goes to Paris to take this, his final year of undergrad in fashion design, and comes back and is suddenly diagnosed with an aggressive glioblastoma multiforme, which is one of the most horrible tumors of brain tumors. And this 22-year-old boy, 16 months it took him to die a tormented death in which he's quadriplegic, he can't move anything, he can't even swallow. And his friends like Scheherazade, my daughter, and two other best friends, Rebecca and Charles, wouldn't leave his bedside and watch all the ravages of this savage disease, what it can do to you. All those experiences, you know, have somehow snatched innocence from these poor children and pressed their faces against the pains of grief and mortality at such a young age. So those things, affect you in ways that you don't realize even when it's happening, of course, because this is going to take years and years. And ultimately, Freud is right that the final answer is that there is no answer. The final solution is that nobody is going to be able to explain to her that Andrew didn't deserve it, what happened to him. Nobody can explain why such a painful death for this 22-year-old gorgeous boy. So it has shaken her so much that she started, she did her undergrad at Columbia and wanted to be a doctor, but then became interested in science journalism. And is now more interested in, then became very interested in early detection of cancer. And she was working as a journalist with the company there, but realized that she would rather be telling the stories properly. So she is now going to graduate school to do script writing and filming. But to answer your question, Ira, I must say that I feel very sad for someone whose childhood was snatched and whose early entrance into adulthood has also been constantly engaged with this fearsome challenge of the other. And the other in this case is cancer. Somehow it has infiltrated every part of our life. And the question of mortality, which most of us don't even think about until we are middle-aged at least, those questions are very up front and center for someone like her. And I'm just hoping, sorry to give you such a long-winded answer when you ask me, how's your daughter doing? I mean, the answer is that only time will tell how these soul-shaking, soul-destroying experiences will allow her to tell the stories of humans who suffer at many levels in a way that convey this, the silences, the things that are not talked about. Those kinds of things, will she be able to relay them or not? I think only time will tell. At the moment, I think she is trying to come to terms with all that has happened.
Appreciate you sharing that. It's been a very insightful and inspiring hour that you've spent here talking about this journey and everything you're going to be doing to keep moving it forward. And just really appreciate your time. For everybody that's going to be listening on the podcast or watching on the YouTube channel, you've been listening to the amazing Dr. Azra Raza, Soon-Shiong Professor of Medicine, Department of Medicine, Division of Hematology-Oncology, Director of the Myelodysplastic Syndrome Center at Columbia University Medical Center. Please look for her book, The First Cell and the Human Cost of Pursuing Cancers Last. Dr. Raza, it's been an honor to spend this time with you, to meet you. And as we say, thank you for not just everything you're doing and you've been doing, but thank you for creating possibilities of a better tomorrow. It's been really a wonderful time spending with you.
Thank you very much, Ira, and thank you to all your audiences.